Look at any large span building, a stadium, a bridge, or even the roof over your head, and you'll see a repeating pattern of triangles. In construction, this is known as a truss. But why triangles? Why not squares or arches? Today, we're breaking down the engineering and the efficiency of the truss. At the end, say subscribe and follows in Crete.
You see them everywhere, from stadium roofs to highway bridges. But what actually makes a truss a truss? Let's look at the anatomy. First, we have the chords. The top chord acts like a shield, usually taking the brunt of compression or pushing forces. The bottom chord acts like a tie, handling tension, the force trying to pull the structure apart. Between the chords is the web. These are the diagonal and vertical members that create those iconic triangles. Their job? To transfer the load from the top to the bottom and keep the chords from bending or buckling. Where these members meet, we find the nodes. In wooden trusses, these are held together by gusset plates, steel connectors that stitch the wood together. In steel trusses, these nodes are often welded or bolted. By arranging these parts in triangles, the truss becomes a rigid unit that is lighter and stronger than a solid beam. That's the power of geometry. That is the anatomy of a truss. Subscribe and follow.
When it comes to efficiency and tradition, one design stands above the rest: the king post truss. It's the simplest form of truss, and it's been a staple of construction for centuries. At its heart, the king post truss is a simple isosceles triangle. It consists of two principal rafters and a horizontal tie beam that prevents the walls from spreading apart. The star of the show is the king post, that central vertical member. Contrary to how it looks, it doesn't just sit there. It's actually in tension. It grabs the center of the tie beam and pulls it up toward the apex to prevent it from sagging over time. For slightly wider spans, we add struts. These diagonal braces provide extra support to the rafters, making the structure even more rigid without adding heavy bulk. Because of its simplicity, the king post is perfect for spans up to 8 meters. It's cost-effective, easy to build, and looks great in exposed beam ceilings. Simple, strong, and timeless. That's the king post. Subscribe and follow.
If you're looking at a bridge and see a series of V shapes pointing toward the center, you're likely looking at a Pratt truss. Patented in 1844 by Thomas and Caleb Pratt, this design revolutionized construction. Its signature feature? The diagonal members slope downward and inward toward the center of the span. Here's where the magic happens. In a Pratt truss, the diagonals are almost exclusively in tension. This is a huge advantage because steel is incredibly strong when pulled. Meanwhile, the shorter vertical members handle the compression. Because they are shorter, they are less likely to bend or buckle under the weight. This smart distribution of forces means you can use less material to span much longer distances, sometimes up to 75 meters. It's the lean, mean, weight-bearing machine of the engineering world. You'll find Pratt trusses in everything from 19th century railway bridges to modern industrial hangars. It's reliable, cost-effective, and easy to build. The Pratt truss, making long spans possible for nearly 200 years.
If the Pratt truss is the king of modern steel, its ancestor, the Howe truss, was the king of the railroads. Let's look at why it's built differently. Patented in 1840, the Howe truss is easily identified because its diagonal members slope up toward the center. This is the exact opposite of the Pratt design. Here's the engineering logic. In a Howe truss, the diagonals are in compression. Because they are under pushing forces, they are typically made of thick wooden beams. The vertical members are in tension, so they are often made of iron or steel rods that pull the chords together. This design was a game changer in the 1800s. It allowed builders to use heavy, locally available timber for the bulky parts and expensive, high-strength metal only for the thin vertical rods. It's the ultimate hybrid structure. Today, you'll find the Howe truss in heavy-duty girders and historic bridges where massive downward loads are the norm. It's a testament to how material choice dictates design. That's the Howe truss. Subscribe and follow.
If you've ever looked at a house being built, you've seen this truss. This is the Fink truss, the most popular roof structure in the world. It's instantly recognizable by its internal webbing. Unlike simpler designs, the Fink uses a W pattern of diagonal members to break the span into smaller, manageable triangles. Why is it so common? Efficiency. This W configuration allows the truss to handle heavy roof loads, like tiles and snow, using smaller, lighter pieces of timber. It gives you the highest strength-to-weight ratio for mid-sized spans. Because a Fink truss can span up to 14 meters without needing any center support, it's the secret behind open-concept floor plans. No interior load-bearing walls required. They are prefabricated, easy to install, and cost-effective. While they don't leave much room for an attic, they are the reliable backbone of modern homes. The Fink truss, building the world one triangle at a time.
Trusses are engineering marvels, but their success comes down to two things: what they're made of and the massive benefits they bring to the job site. In residential builds, timber is king. It's affordable, sustainable, and easy to handle. For massive spans like arenas or bridges, we turn to steel. Steel trusses offer incredible strength-to-weight ratios and can be bolted or welded into complex, custom shapes. The biggest advantage? Span. Because trusses distribute loads into tension and compression, they can span huge distances without needing support pillars. This is how we get those wide-open, no-column interior spaces. Lighter, stronger, faster, and cheaper. Whether it's wood or steel, the truss is the smartest way to build up.